Hi, everyone. I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy journalist for over 20 years. I like to bring you behind the scenes, talk to the researchers who are doing the work that's bringing us all the cool news about space and astronomy. Today, I've got Dr. Sam Howell from NASA JPL. Hey, Sam, how's it going?
It's going really good. I'm happy to be here.
So, tell people who you are. What do you do?
Yeah, as you mentioned, my name's Sam Howell. I broadly study planetary interiors and geophysics. Once upon a time, I did seafloor geology on Earth. And then in grad school, I attended this lecture by another grad student on how there were these alien notions orbiting Jupiter with their own kinds of icy plate tectonics in the shells. And I thought, that's way cooler than the thing I'm doing. So, anyways, we're married now, and we both work at JPL. And
Right.
I study the ice shells of moons like Europa and Enceladus that have these global subsurface oceans. I also work on their future exploration. So I am a project staff scientist on NASA's upcoming flagship Europa Clipper mission. The Project Science Office works to help bring together the science team and ensure the scientific success of that mission. And then I also work a lot of my time in potential future concepts to actually get through the ice and take a look under the ice shells at the oceans in situ.
So, how did we first discover or theorize that there was some kind of liquid ocean underneath the surface on Europa?
Yeah. So I'll start by saying Europa, we're beginning to understand that these ocean worlds are pretty common in our solar system, at least at Jupiter and Saturn. There's every reason to expect we're going to find them at Neptune, and maybe even things like the asteroid Ceres and the Kuiper Belt object Pluto. Though Europa had the first discovered planetary ocean, and it was pretty unexpected. Jupiter itself has a really strong magnetic field. And that magnetic field varies a lot in time and space. And so when the Galileo spacecraft in the late 90s and early 2000s was at Jupiter, one really surprising thing is it was going around Jupiter, measuring that varying magnetic field, it would see these blips as it passed Europa. And it turns out that Europa is doing something really similar to like wireless chargers on your phones, where a wireless charger has a coil of wire and you put an alternating electric current through it, and that makes a magnetic field. And on your phone, you have another loop of wire, and that magnetic field becomes a current again. Well, as Europa went through this big varying magnetic field at Jupiter, it actually started to charge and induce its own magnetic field back. And so the only way that that's possible is if there's a big loop of wire somewhere, if somewhere there's a globally conducting, electrically conducting layer. On Earth, you might expect that, our magnetic field comes from a big globally conducting layer in our outer liquid core, but that's not really something we expect on Europa. And so the most plausible early explanation for that induced magnetic field, the response of Europa to Jupiter's magnetic field, was a global salty ocean. Since then, there's been a lot of evidence that's piled on, geologic evidence, evolution in our understanding of where Europa gets its energy, and how it could support an ocean over long periods of time. But yeah, we really got the first confirmations that we were relatively certain of an ocean at Europa from its magnetic field, from the fact that it was kind of responding back to Jupiter's own magnetic field.
That's really surprising. I had thought that it was visual evidence of the surface of Europa, seeing how crater-free it was and how it looked like there was some kind of resurfacing event. And I'm sure that's some of the additional lines of evidence, but that it's interesting that incredibly strong first piece of evidence that you've got this connecting magnetic field. That I had no idea. That's
Well, so
neat.
you're right that from the early geologic evidence, people had theorized that maybe Europa could have enough heat that water ice could stay liquid, right? The Voyager missions, as they passed through the Jupiter system, were really incredible. That we had kind of thought moons looked like our own moons. Pioneer 10 had been out through the Jupiter system and gotten a look, but we really didn't expect to find, these active satellites of very fiery and volcanic Io closest to Jupiter. And then, as you mentioned, a very geologically active Europa that was chocked full of water ice next door. And so folks had started thinking early on about whether or not global oceans could be supported, but the sort of smoking gun was that magnetic signature. But it's interesting that you mentioned the resurfacing, because right, that's also a very important part of the story of Europa. In that, when you look at the surface of Europa, there's really no craters, and there's not many craters on Earth when you compare it to the moon, and that's because we have things like plate tectonics and erosion that are constantly changing the surface of the body. Well, Europa doesn't have an atmosphere, so there's not really erosion, but what it does have is a bunch of things that look kind of like plate tectonics. And the result is that the average surface of Europa is probably on the order of 60 million years old, which sounds old, but that's much younger, for example, than the average age of the Earth, where we have all this erosion and plate tectonics going on.
So what, with Europa being sort of one place and a very exciting location, what made astronomers, planetary scientists start to think, okay, actually, all of these icy worlds could very well have liquid water underneath?
Well, one of the biggest changes in that thinking was understanding how these bodies interact with the giant planets they orbit. So usually a world doesn't have a whole lot of heat to deal with. Maintaining heat is especially important if you want to have geologic activity. The warmer things are, the easier they are to reshape and to move around. And as you siphon off that heat energy to space, you can do some useful work with it and make some faults and fractures and things. So when we think about how you keep a liquid ocean liquid, a lot of the early thinking was focused on something called radiogenic heat. And so from the cloud of dust that formed our solar system, there were a bunch of highly radioactive elements, and those were incorporated into all the rock the planets are built out of today, and provide sort of a long-term, very low-level heat, probably not enough to keep liquid oceans liquid. And so it wasn't thought to be, the most plausible across the solar system. But what we know now is that as, for example, Europa orbits Jupiter, its orbit is kind of egg-shaped. It's not a perfect circle. It's what we call an eccentric orbit. When Europa gets closer to Jupiter, it kind of squeezes towards the body as it feels Jupiter's pull get stronger. And as it gets further away, it kind of relaxes and goes between more of a football and more of a sphere. Because Jupiter is a little bit bigger than our own moon, whereas the moon makes tides of, a few meters in the ocean on Earth. The solid tidal wave traveling twice a day around Europa is probably 30 meters or about 100 feet.
Wow.
And so, these are really massive solid tides. And as you move and deform the ice with that tidal wave, it releases a lot of frictional heat. And so we're learning now that the different layers of these bodies use some of their gravitational energy with worlds like Jupiter and Saturn to deform and make frictional heat as they go around, and that helps keep a lot of oceans. So in the Jupiter system, we think really that tidal interaction is what keeps things warm. And as you get further away, or as your orbits get less eccentric, you rely more on that tidal heating. So at the very edge of the 4 Galilean satellites, where we have Io closest to Jupiter, and then Europa, Ganymede, and Callisto, Callisto might not have much of the frictional tidal heating left, and so it relies a lot more on just that natural long-term heat. And so the same ended up being true at the Enceladus system, at the Saturn system with Enceladus, right? Enceladus is a very tiny moon. It's half the size of the Minor Planet series. If you're familiar with the geography of California, you could fit it between LA and San Francisco. And so because it doesn't have much mass, we don't expect it to have much long-term heat. But what we understand now is because it's very small and its gravity is very low, only about 1% of Earth's, that its rocky part is just kind of a rubble pile. And that rubble pile is very easy to squeeze as it goes around Saturn. And so for Enceladus, it's the same story, that a tidal wave traveling around that rubble pile at its core generates a lot of heat every day and keeps the oceans liquid. And so when we think about where oceans are possible in the solar system now, it's really become a conversation of where are there long-term sources of heat, and we especially focus on these gravitational interactions.
And so if you were to like slice open a generic world in the solar system that has this source of heat,
Mm-hmm.
what would the layers look like, do we think?
Yeah. So I think about Europa as being like the classic ocean world. If I was making an ocean world picture for an encyclopedia, I'd start by slicing Europa open. I'll start at the center. Europa may have an iron core, or iron and some lighter elements like sulfur, like we find on Earth. But it probably is not liquid on the outside like we find on Earth. It's probably solid. Then you have a rocky mantle, and that rock is very similar to the rock that Earth's mantle is made out of, most likely. It's likely primarily silicates, and where the core might be a couple hundred kilometers thick, the mantle is probably on the order of 1,000 kilometers thick. So little core and big rocky part. And then sort of just as a skin on that rocky part, you have the water part. And so Europa has a global seafloor. On top of the rock, there is sitting an ocean that's probably about 100 kilometers or about 50 miles deep. And so that's, 20 times as deep as Earth's average ocean depth. And then on top of that, there is an ice shell. Turns out oceans really don't like being exposed to space where the temperature is only 90 degrees Kelvin above absolute zero. And so they form some ice to insulate themselves from the space environment. On Europa, that ice is probably around 10 miles thick. We tend to think somewhere between, about 10 and tens of kilometers. I like a number right around 25 kilometers, which is just about 10 miles.
Yeah.
But the interior structures of these worlds can vary a lot. If you were to go slice Ganymede in half, it would be a pretty similar story, except Ganymede might have a liquid outer core. Ganymede is unique among all of the satellites of the solar system. It is the only one with its own magnetic field. So not this response to Jupiter, but like Earth, it creates its own. And because Earth does that with a liquid outer core, we think Ganymede probably does too. Ganymede is huge. It's bigger than the planet Mercury. And so while Europa is the size of our moon, Ganymede's the size of a real planet. But the structure is pretty similar. You have kind of iron and some lighter elements, and then you have, a little over 1,000 kilometers of rock. And then on Ganymede, you might have a very deep ocean, several hundred kilometers. And something that's kind of cool is because it's a little bit bigger than Europa. It's like the size of Mercury, and its gravity is a little higher. The pressures at the seafloor get high. And turns out there's a lot of different kinds of ice. There's not just the kinds of ice that you form in your refrigerator, which is the ice that like Europa's outer ice shell is made of. But at very high pressures, you can form different ices. And so Ganymede's seafloor is probably covered in this interior ice shell that of unknown thickness, where you have this high pressure ice layer, and then a deep ocean, and then another ice shell on the surface.
Right.
If you go to Titan, it might have all of those layers in the Saturn system. It might have all of those layers, and then it has an atmosphere on top. And on top of the water ice shell on Titan, you have liquid hydrocarbons like methane that, just like Earth, form clouds and rain and lakes and rivers. And all of that is happening on top of an ice shell, which is happening on top of an ocean, which is happening on top of an ice shell, which is happening on top of rock, and then maybe a core. So really, though, the story is, if they have a core, you got some metal and then some rock, ocean, and ice.
But even if you don't have like this active tidal interaction with a giant planet, just the radiative heating from the radioactive elements inside of it, do you think that's enough to supply all of the icy objects with some kind of interior ocean?
So not all of them. Most of the icy worlds are more similar to Enceladus. If you go to the Saturn, so if you're at Jupiter, you have the 4 main moons discovered by Galileo in like 1610. Well, we call them the Galilean satellites. Galileo was the first to publish. Someone else might have seen them first. I think there's a lesson in there for future scientists.
Yeah.
We don't call them Simon Marius's satellites, but
didn't
so
he
Jupiter's
name them after Galileo? I forget. Like
so we call them the Galilean satellites because in his little journal he sketched these 4 little stars with Jupiter at the center, and this really helped him understand that objects in space orbit each other. So Galileo and Simon Marius probably saw them at about the same time. Galileo published a couple years earlier. And there was also confusion because Marius was using a different calendar, so people thought he was really later to the game than he was.
Right.
So there'll forever be an argument over who found these satellites. Also, there's some argument that they were discovered in the 4th century BC, or AD, I mean.
With some really good eyesight.
Yeah, really good eyesight. So always publish your findings as quickly as possible.
Right.
Anyways, the Galilean satellites, they're all big, right? Europa and Io are like the size of our moon, and Ganymede and Callisto are like the size of Mercury. But if you go out to Saturn, it's a very different story. You have, moving out from the body, the ring system, and that, could be an icy satellite like Enceladus that's been pulled apart by Saturn's gravity. Or maybe instead rings migrate out and form bodies like Enceladus. But you have all of these small icy worlds that are much more close in size to minor planets or asteroids than they are to the Galilean satellites. And so there's Mimas and Tethys and Dione and Enceladus. Much further out, there's Titan, which again is like the size of Mercury, but it's there's no other body like that in the Saturn system. So, and most of them are small. We expect that if we go to Uranus, for example, most of those are going to be small icy satellites. The issue is that in order for the radiogenic heat, that sort of primordial heat left over from the formation of the solar system, in order to have that radiogenic heat be meaningful, you need to have some of it. And these bodies are just too low in mass to really retain a lot of those radioactive elements. So because they don't have much of that heat, it's much harder to sustain an ocean. There are probably a lot of these bigger worlds that are capable of sustaining oceans only with the radiogenic heat. But it really seems that on the worlds where we're finding oceans and we're finding ongoing geologic activity or recent geologic activity like Europa and Enceladus, it really seems that the tidal heating is one of the most important parts there.
So, the excitement, thanks to Enceladus and the geysers that are coming out from the tiger stripe regions from the southern pole, you've got this exciting proof. I mean, that feels like that's the smoking gun, the vaporizing gun that's producing this material. Why do these seem like very exciting places to search for life in the solar system?
Yeah. Certainly the stripes of Enceladus are incredible. And you're right, the most plausible explanation is that they are somehow in contact with a global subsurface reservoir, which very well may be the global ocean. So I'll talk first about, why Europa. NASA has this flagship habitability mission coming up, which will orbit Jupiter to target Europa specifically to investigate the body to understand its habitability. The reason we're focusing on Europa is that it seems to have all the elements that result in life on Earth. And what I mean is the ocean of Europa is probably long-lived, billions of years old. And so you have a lot of time. We also have a lot of heat. Europa's interior heat and the tidal heat from the ice shell are probably enough to keep things like ongoing geologic activity on the surface of the icy part, but also ongoing geologic activity on the seafloor. When we think about how life emerged on Earth, we tend to look at environments that can be very similar to Earth's hydrothermal vents. At the seafloor of Earth, you can have water that percolates down into the rock and then gets very hot because it's in contact with very hot rock. And so much like hot air rises in a balloon, the water rushes back out again. And as it does that, it dissolves and collects minerals, and it makes these really beautiful chimneys called vents, where all of that mineral energy is concentrated. And so that's one example of a place on on Earth where we think life might have emerged. Europa probably also maintains ongoing activity at its seafloor. There are some really exciting new papers out that show even to present day, there could be volcanism at the seafloor of Europa. And so the first really important part of the puzzle is that you have a large amount of time and an energy source. But just the vents alone don't do it for you. The reactions between the water and rock, we say, are reducing, and they make one half of an equation. On one side, we have reductants, which want to give electrons up. And on the other side, you have something called an oxidant, which wants to get them. And all life that we know of on Earth exploits that process. All of us are just waiting for a reductant and an oxidant to come together. And kind of like how when you buy a car, you have to go to a car dealership. You can't just go straight to the manufacturer, and the car dealership takes a little bit of the profit off the top. That's how life works. We wait for an electron to move between a reductant and an oxidant. We take a little bit of the energy off the top, and then we let the reaction happen. So on Europa, we have a lot of water rock reactions that give us half the equation inside the ocean. The other half is, I mentioned Jupiter has a really strong magnetic field. Well, that also means that it traps anything with a charge that comes its way. So charged particles from the solar wind, for example, will get trapped in that magnetic field. Or Io, which is extremely volcanic and the closest moon to Jupiter, spews these charged particles out of its volcanoes. And it can spew them with enough force that they actually go into orbit around Jupiter and they get trapped. And so all of these charged particles are traveling around this magnetic field, accelerating faster and faster. And they form a kind of radiation. This environment is really, really strong at Europa, which initially seems bad for life. It's a very strong radiation environment. In fact, the biggest challenge of going somewhere like Europa is the extreme radiation environment. But it's good for life, because if you take some of that stuff from Io and you stick it on ice and you blast it with this radiation, you get oxidants out. And the missing piece of the puzzle is that, as you mentioned before, no craters on Europa, very few craters on Europa, because it looks like somehow it's capable of, like Earth, taking its surface and bringing it back down into the interior. So
sorry, I just want to just clarify this. So,
yep.
This idea that the radiative environment is blasting the surface of Europa and assisting in creating this electron, I guess, positive, negative, bringing these two halves of the equation together. But I also know that ice is a very good way to protect yourself from the radiation from space. A meter under the ice, you're pretty safe from cosmic rays and the solar wind. So is there some kind of mechanism that is carrying this into the water, or is this a separate location from something that's, as you say, 10 kilometers under the ice? That's a long journey to try and communicate between the two.
Yeah, I think that's a fantastic question, and it's the reason you have to hire somebody like me. So on Earth, I studied plate tectonics processes of how material from the rocky mantle gets to the surface and is recycled back down. Right, and so we've set up this problem. Half of your meal is sitting on the surface of Europa, and the other half is in the ocean, and you're separated by 10 miles of ice. And you're right, the radiation probably penetrates 10 centimeters rather than 10 kilometers. But when we look at Europa, we see a lot of signs of recent geological activity. much like Earth, there are signs of things that can move material as solids. Like on Earth, we have subduction, where tectonic plates will get pulled back down into the interior. And so you can imagine after coming up and loading your backpack with oxidants, you get pulled back down into the interior and into the ocean. There's also some evidence that there may be the production or intrusion of shallow liquid water on Europa within a few kilometers of the surface. If you look at the body, it looks totally destroyed by what we call chaos terrains, and they're named that way because they just look very chaotic. The surface is all jumbled up, and you separated by this kind of knobby fine texture. And some researchers have intuited that an explanation could be the drainage of water from the surface. And so whether it's in solid state or in a liquid state, there's evidence that there's downward transport of material on Europa. In sort of the limiting case, where maybe you don't have a whole lot of melt drainage from the surface to the ocean, or you don't have a whole lot of material getting pulled down through like subduction in the ice, nothing on the surface of Europa looks as old as the solar system. And so it looks like the entire surface, at least on the order of 50 or 100 million years, gets replenished. That surface has to go somewhere. So the limiting question might be, how good are your lungs if you can only take a breath every 50 million years?
Right.
I don't know that the answer is they're bad, but there are also there's a lot of evidence for ongoing and recent geologic activity that could make that a more continuous process.
But you're saying that you've got like one process potentially coming from the surface, but also potentially the energy that's being supplied at the geological, with their black smokers at the bottom of the European Ocean. So both are contributing potentially to increasing the energy potential inside the European Ocean.
Absolutely.
Yeah.
And there's kind of two cases you can think about. And it depends on who gets more material into the ocean. If the oxidants are just coming down all the time in a really big volume, you might imagine that there's plenty of those available to eat. And so you're really waiting on some of the reductants to show up to finish your meal. And so in that case, you might, which is, we think, more similar to early Earth around the time life emerged, you might be hanging out on a black smoker waiting for those reductants because you have all the oxidants you can eat. If you have way more of the reduction happening, so like say it's been a while since your last meal from the surface, you can imagine like the little cartoon behind me with the purple splotches, that there might be things waiting on the base of an ice shell for a little bit of oxidants to come down to finish their meal because they have plenty of the other stuff in the ocean. And so, the really important part about making this kind of equation for life happen at Europa is the recent geologic activity. Like it really brings these things together. And the story is different for every ocean world.
Well, it feels to me like Titan, when you think about Titan with that layer of hydrocarbons on top of it, if it's undergoing the same process, not only do you get the reactants and the oxidants, but you're also getting this infusion of organic chemicals into the mix as well, which is like next level exciting.
Yeah, I really think Titan is a fantastic body. As you know, NASA has selected an octocopter to go there and fly around the organic dunes, and the Dragonfly mission is going to be truly spectacular. It also is a head scratcher for me. So I've gone from sort of theoretical, thinking about the geologic behavior of theoretical ice that I program in Python, in thinking more about how real materials work. And I've gotten to the point where I can wrap my head maybe around water plus table salt. And so you get somewhere like Titan, and you have all of this organic chemistry and all of the water processes and all the electron exchange processes. I think there's a a lot of exciting potential there for interesting chemical reactions.
It would be incredible.
And I think some of the major questions for Titan, though, become, do you get material across the ice shell? It's harder there because the ice is thicker. Or does it matter? Can you do it all with just the ice and organic chemistry on the surface?
Yeah, I can imagine, like, if the dragonfly can find like a fault where, like, a subduction zone where ice is, or material is definitely going down under the surface on Titan, that kind of thing would be exciting. Well, let's talk about the Europa Clipper as a way to study this further, but I also want to spend a lot of time talking about how we could practically get down under the ice and investigate it. So, you mentioned briefly about the Europa Clipper. Where, how will the Europa Clipper help us further this, our understanding of what the environment is like at Europa?
Yeah. So, quick overview. It's a large directed mission by NASA with its radar antenna and solar panels. It's, I think, by length, probably the largest planetary probe that's been built. If you put it on its side, it would go from just about the toes of the Statue of Liberty to her crown. So it's big. What we're going to do is launch in October of 2024.
Which is right around the corner.
I know. It's a very exciting time. Hardware is starting to show up. Things are crystallizing into a real spacecraft. It's super exciting. So the plan is to launch in late 2024. And we'll arrive sometime in early 2030 at Jupiter. But it takes some time, right? We're traveling at interplanetary speed. So it takes a minute to slow down and really get down to Europa. We toss some of our momentum into Ganymede, and maybe at the end of 2030 or in early 2031, we're studying Europa. Like I mentioned, we orbit Jupiter to fly by Europa. That's because of the intense radiation environment. So we just kind of dip our toes into the radiation and fly back out again. And the way it's going to help us understand the structure and the habitability is kind of fourfold. The overarching mission goal is to explore Europa to investigate its habitability, but there are really 4 science objectives within that. We're going to explore its ice shell and ocean, including constraining the thickness of the ice shell and the salinity of the ocean. We're going to explore its composition, its geology. As we've talked about, the active geology is a really important part of how we understand how material moves, and also its current and recent activity. And so it's a really diverse payload of instruments. We have compositional spectrometers and thermal spectrometers. We have an ice penetrating radar that's very exciting. So we'll be able to see a lot of the different icy faults and subsurface structures, or if there's water in the ice shell, we might get really interesting reflections from that. We'll also be doing science based on the gravity field around Europa, which will help tell us where the different layers are and how thick they are. And so, sort of, as we've already talked about, bringing all these lines together of where is there energy, how much energy is there, and how does it move from point A to point B, feeds into this story of, the structure of the world, its chemistry, and its potential habitability.
So what would you be looking for? Like, for your specific interest, what kinds of features would you be looking for on the surface or with any of that data to give you a sense of, our chances of European space whales?
Space dolphins.
Space dolphins, sure, fine. Yeah, I mean, you may be a fan of space dolphins. I think they're space whales. I'm sure we can meet somewhere in the middle.
Yeah, I mean, they're both mammals that mistakenly went back to the ocean.
Sure, some kind of space walrus.
There you go.
But what kinds of features would lead you to believe that things are shaping up nicely for Europa?
I think that for me and the way I view the habitability story, for me, there are a few things. First, learning what the heat budget of Europa is. As I mentioned, heat, whether it's radiogenic or tidal, is really what allows us to do useful things like melt ice or concentrate chemistry, or even do the geology that we see on the surface. And we'll get measurements that will help us understand how much heat is flowing out of the surface. And you can imagine then if you take the whole surface and you add up how much heat is flowing out, you know how much heat is available to do stuff with. That's something I'm very excited about. The sort of another major interest is understanding how thick the ice shell is. So maybe surprisingly, if the ice shell is relatively thin, there are some worlds in which that actually makes it harder to move things across it. And that is because as an ice shell gets thicker, around 25 or 30 kilometers, you get this process that starts that we see in Earth's mantle called convection. And so the solid ice sitting on the ocean is pretty warm. And like hot air, it wants to rise. And the ice sitting up near the surface is pretty cold. And so it wants to sink. And you can actually get this solid process that happens over tens or hundreds of thousands of years, but that allows material to consistently be exchanged between the surface and interior.
So it's like a lava lamp, but ice.
Yes, a lava lamp of solid ice. It works exactly the same way.
Wow.
Right? Wax gets hot, goes up, cools, and comes down. And so that kind of process really helps you continue a long-term exchange, especially from the surface downwards. So as we learn more about the structure of the ice shell and sort of the range of potential processes, that's very exciting. But for me, something I can often be skeptical of, but the thing I'm most excited to get there and find is shallow subsurface water. If we find that there are active regions of chaos that are, associated with water that's near the surface, that's a really great way to exchange material. If the water formed where it is by melting, it can drain down and bring material with it. There's a lot of cool work in that field. Or if the water was somehow pushed up and a conduit from the ocean, then that can help bring material upwards. And so I think the short odds are, for me, are thinking about the ice shell thickness and the heat budget and where we get the energy to move things around. And whether we get the energy to sustain these chemical reactions on the seafloor for, since Europa was born. But also, I'm really hoping that we find water everywhere.
Right.
And maybe, even though I mentioned at the beginning, I like about 25 kilometers is the answer for the ice shell thickness. We don't know it very well. It could be 5 or it could be, 80. But I would also be very excited to find out that the ice shell's maybe 5 or 10 kilometers thick. I don't think it's the most likely thing, but if it were, then there are a lot of really new, interesting processes that become possible. Like maybe you crack stuff and have eruptions through the cracks and all sorts of other fun things.
And so how deep can Europa Clipper accurately map out the subsurface ice?
That depends entirely on how much the ice cooperates. So it really depends, depending on the wavelength of the radar, and we're bringing 2, one for more shallow sampling and one for deeper sampling. That signal can fade away deep in the ice shell, especially if it's warm, but also especially if it's warm and a little bit wet. Ice does this really weird thing that when you get it near its melting temperature, tiny little micro pockets of water start to show up, even if you don't start melting it. And that can be bad news for radar. But there are lots of considerations like salt and porosity, how fluffy the ice is, that feed into how deep we can see and kind of what the resolution we can see in depth is. But, all of that said, if you go and have a conversation with the radar folks, they're pretty excited about the depths they're going to see. Yeah. If Europa cooperates and the ice shell is relatively thin, there's the potential even to see to the ocean.
I mean, there's been some really impressive work even done on Mars where people are turning up liquid oceans under the regolith at the North Pole. Although maybe it's clay, but maybe it's water.
Yeah, maybe it's clay.
But still, that they're able to do this, and they never had sort of originally planned or intended this kind of capability. I'm always impressed and never surprised, I think, when people are able to push their instruments farther than they'd ever planned. Once it's actually operating in the field, they start to fine tune things and change their techniques, and it's kind of surprising. All right, let's talk about getting under that ice, which is sort of the whole point of this conversation. We had this prelude, but what you're working on is of tremendous interest to my audience. It comes up all the time when we talk about Europa. There's a lot of eye rolling and but we'll never be able to get under that ice. And I say, no. There are some really interesting prototypes, some work that's being done right now, places here on Earth. This technology is being tested. How are you actually testing out getting under this kind of ice?
Yeah. I'll start by saying that I get the eye rolls too. Even within this community, and I think that there's this perceived difficulty to the problem that really we actually understand pretty well. So the first answer is, you might imagine somewhere like Mars, where we have trouble getting down, on the order of a meter. The really nice thing about ice, though, going back to our conversation about heat, is that we know how to melt it pretty easily. And so most of the technologies are focused around what we call melt probes. It's a pretty self-explanatory name. And these are a class of cryobot, which are robots for the exploration of cold, icy places. So the very first cryobots were developed on Earth in the 50s and 60s. And as long ago as the late 60s, people like these, in my field, foundational researchers, Amat and Filberth, were getting probes 1 kilometer deep in Antarctica. And so 1 kilometer doesn't sound like 10 kilometers, but because Europa is only 1/10 of Earth's gravity, it's actually about the same pressure. And there's been 50 or 60 years of development of melt probes since then. After the discovery of Europa's ocean in the late 90s, early 2000s, a lot of folks thought about, okay, how do we get inside? And it's one of the very first things I engaged with when moving over to planetary science, and remain thrilled about it. So I'll talk a little bit about what we're doing on Earth, and I can also talk about, what we think these vehicles could look like for space.
Yeah, and definitely, let's practically, these things exist. This is only marginally rocket science.
Yeah, exactly. In fact, we have what we call a rocket equation for melt probes.
Really? Oh, okay. All right.
Yeah.
So what does your kind of classic melt probe look like, and how does it function?
Yeah, if you're a classic melt probe on Earth, you essentially have a electric generator at the surface and a long copper wire that goes down into something that looks just like a tube. And in that tube, there's electrically powered heaters. They work just by being really poor conductors of electricity. So you put a lot of electricity across them, and instead of giving that electricity back, they just generate a lot of heat. It's something that is normally referred to as like a hot penny melt probe, where you can imagine just sticking a torch on a penny and then dropping it on a cube of ice.
Right.
So that was for these early classic designs, it was just heating from electrical power from the surface. And there's definitely different ways we would have to approach power in a planetary environment, but melt probes on Earth are now widely varied. Many of them still use electrical heating. Something that folks at like Stone Aerospace have been doing that's very cool is you can actually take a laser from the surface, and instead of a copper wire, you put the laser down a fiber optic cable, and that at the bottom hits a metal target that warms up. And so, it's this kind of work is going on all over the country. JPL, but also at companies like Stone Aerospace and Honeybee Robotics, and universities like Georgia Tech and Cornell and Johns Hopkins. And so there are a lot of people that really believe in these technologies. Okay, melt probes, electrical heating.
Right.
There's a second component that helps you deal with things like stuff trapped in the ice, like dirt and rocks, called water jetting. So in a water jet, you're melting the ice around you, and you have some water available. So you bring that in, you heat it up with your heater, and then you shoot it out the front. And that kind of helps you move all the heat to the front, but it also helps stir up anything that's stuck in front of you. And also there are several concepts that are, especially for planetary environments, considering cutting. If you happen to run into a really salty layer or something that's difficult to melt through. So on Earth, there's a lot of great field work going on to test these melt probes. Recent work has shown like some cold glacier descent in Greenland. There's been some recent work on transversing through dirty ice. And a few weeks ago, NASA recently selected a project that I'm leading as the principal investigator. We're calling ORCA, which is using a melt probe developed at the University of Washington called Ice Diver, which will have a water heater and water jet, or sorry, a heater and water jet on board to access a subglacial lake in Alaska. So a lake a few hundred meters beneath the surface. And we're really now on Earth starting to think about, as you're going through the ice, what do you actually do? And so something we're going to be doing is we're going to be bringing in that water as we go through the glacier, but we're not just going to be using it for heating. We're going to pump it back to the surface into a bunch of analog planetary instruments, but also take it back to a glacial microbiology lab at the University of Tennessee, Knoxville. And we're going to use our probe moving through the ice to understand the distribution of life in that ice, as well as the context of like the chemical environment and things.
But essentially, you've got it looks kind of like a rocket. It's got a pointed front, pointy side down in this case, and you let gravity do your excavating, and it's just because it's so hot, it is melting in front of it, providing this kind of liquid area around it, and then freezing behind it in some cases, and in other cases you're trying to keep the borehole open and you're able to test it. But I'm assuming as you go 10 kilometers down in the ice on Europa, you're going to need to keep it's going to be freezing behind you as you go.
Yeah, when you're a couple probe lengths down on Europa, it's frozen behind you. So yeah, that's exactly it. It's a big pointy nose.
Yep.
If the ice is freezing behind you, you need to make sure that you're carrying the umbilical back to the surface on the probe, right? If it's frozen in the ice, you're not going to be able to lower it down. And so you have to feed it out the back as you go through. That's really what we're exploring for places like Europa. If you're somewhere where the surface is warm, like in Alaska rather than Antarctica, it's pretty easy to keep that hole open. If you go somewhere like Antarctica, where the surface is very cold and it wants to freeze again, people have to do things like put, alcohol down in the hole to keep it from refreezing.
Right. And so let's talk about the umbilical, because again, this is where one of the eye rolls comes from. People are like, that's ridiculous. You can't. How will you communicate with the surface? And so you just mentioned this. You reel your umbilical out from the probe. How big of a umbilical would you need to communicate through 10 kilometers of ice that is frozen into the ice?
So I'll start by saying, with the concept we've been working on at JPL, we call it PRIME, the probe using radioisotopes for icy moons exploration. It's the one, I don't know.
Yep.
You see over my shoulder.
Yeah, that's it. Lodged in the bottom of the ice.
Yeah, we're trying to be robust against a potential 40-kilometer ice shell. And so the answer is you carry a little over 40 kilometers with you. It sounds like a lot, but the only thing that we have to move through that umbilical for a planetary concept is the data. And fiber optics can be very, very strong and very thin. There's a lot of, so the problem isn't so much packing enough to bring with you. The problem is you're on a geologically active world and, your AT&T just strung your internet across the San Andreas Fault or something.
Right.
So it's especially important at the surface where you're extremely cold. You're, like I said, only 100 degrees Kelvin above absolute zero. And every day the surface is flexing back and forth. So you can imagine a little glass filament that's being just bent a little back and forth every day, and it's very cold. And so there's actually a lot of work going on right now to understand how these things could survive Europa conditions. But it's not the only way you can communicate. Something that NASA has recently invested in are wireless communications as well for talking through the ice. And there are a couple different approaches. All of them require that you release and freeze in little transponders in the ice. Depending on the concept, you might find that the number you need is anywhere between, 2 and a dozen. And those can communicate with each other, with the probe and with the surface, either through normal wireless communication like we use, electromagnetic waves, which penetrate really well in the cold upper part of the ice. But you can also use acoustic waves, sort of like little sonar communicators, where you put a physical vibration into the ice shell and you hear it further away. And so when you get to the warmer part of the interior of the ice shell, the radio waves might not travel as well through. It turns out that it's also probably the most solid part. And so the acoustic waves travel pretty well. And so right now we're exploring these different combinations of tethered communications and radio frequency communications and acoustic communications. And the answer in the end is probably, it's going to be some combination of each of these that allows you to be robust against the environment.
So possibly both. Like you're going to have a series of the acoustic ones you're going to be dropping, and they may also be connected by a tether between them that could provide some redundancy.
And I think most folks considering the problem now are considering bringing how you might bring both of those in a future mission concept.
But the point being, for even 40 kilometers of fiber optic cable wrapped in Kevlar is not going to break the back of the spacecraft. You could fit it, you could spool it out, freeze it behind, no problem. Stop.
Yeah, you probably don't wrap it all in Kevlar because as you get past sort of the active upper part, you don't need it anymore. Right. But there are designs we've developed at JPL. There's also designs as part of a NASA Compass study that show what full cryobot architectures can look like. So an architecture in this case means, if you kind of think about the cutaway view, actually fitting all the parts in, but also the connections between them that allow them to work.
So let's talk about the heat source.
Mm-hmm.
What do you think is the best way to provide the heat source that will melt the ice in front of the probe and potentially turn on the grinder if it needs to get through something more complicated than that?
Yeah, I think it's a really great question. For me, I think I'll mention that there are two primary things being considered for a heat source. The first is a little longer timescale, but there have been like nuclear fission reactors, like we generate energy with on Earth, that are being explored for providing power for space missions. You might think about keeping life support going on a Mars colony or something. And so there are folks considering how you might use those at the surface or even incorporate it in a cryobot to get through an ice shell. And so those can be really effective because they produce a lot of heat, but are probably a little further out in the future. What I like to think about are things called radioisotope power systems. So we mentioned earlier that the way these bodies stay warm is they have a lot of heat just from the decay of radioactive elements. Well, we use the same concept today to produce electricity for really deep space missions. Right. When you get beyond the power of the sun, when sunlight really drops off in the outer solar system, you can't bring solar power. And so what we do is we bring these things we call radioisotope thermoelectric generators, which rely on the decay of plutonium-238. 238 just kind of gets hot as it sits there. It is different than 239, which has other uses. And so it uses these little hot bricks of plutonium, and their decay creates heat and space is cold. And so one thing you can do with that is you can use the difference in temperature to make electricity. And that's how things like the Cassini or New Horizons spacecraft get their energy.
Yeah, I mean, there's one on Curiosity, one on Perseverance, the Voyagers.
Exactly.
RPGs are everywhere across the solar system at this point.
So it turns out you can use a very similar approach for cryobots. We explore a pretty classic radioisotope power system as a heat source and find that it does a pretty good job of getting you to the ocean. We have a paper coming out soon on the amount of time it should take, given all of our uncertainties about Europa. But the answer is you probably get to spend a couple years in the ice doing science, so probably somewhere in the range of 2 to 5. But if you have these hot power sources and you put them in the ice, you can't turn off the radioisotope power system. And so you're going to the ocean whether you want to or not.
Right.
Um,
Whether you're still
so
communicating with your probe or not.
yeah, and so there's a lot of questions left in like, how much heat do you need to bring? What's the best shape to put it in? What's the best way to make sure you still get to bring enough science, but also it doesn't take too long to get there? And so there are a lot of these trades that still get made. But, I think we are, I don't think that the heat and the power source are really the thing that would stop us from doing this. I think there's a lot of great thinking in the community on how we could accomplish it for a planetary mission.
And I guess it depends on the cross section of the probe. I mean, I did an article about this a couple of years ago, and it was just like the wider the probe, the bigger the science payload you're putting into it, then the longer it's going to take, because it's just experiencing more friction, as it's more ice resistance as it is and I'm sure, as you said, you've got this rocket equation. So, you've got this melt probe. It's got an RTG on the front. It is melting its way down to the ice. You've reached the ocean, and now you are, as the picture, and people who are listening to the podcast are going to imagine this, there is a melt probe that is now sort of half exposed under the ice shell, and you now have access to the ocean. What comes next?
Yeah. First of all, I appreciate your confidence that these concepts.
It's all gone beautifully.
Yep.
Perfect. Now you have a portal to the ocean.
Yes, and all of the great science that we got the last few years in the ice as well.
Yeah,
to help guide
Nobel
us.
Prizes all around. But now comes the good part.
Yeah, the answer is, I think that you wait patiently. For the reasons we discussed before, you might expect life to want to be near the ice-ocean interface and wait for things to come down. You might have to hope that you're at a place things are coming down and things are waiting. One drawback is that if you come down in the wrong spot, you might not find what you're looking for. So a lot of folks are looking at how you might have mobility of these systems. It can be really difficult to pull off. So let's just pretend you're dangling there. Mm-hmm. The things you really want to monitor are the interface between the ice and then the ocean itself. Its shape, where we might see fluences of different chemistry happening. All of that would be really great evidence to help us understand sort of habitability and how these things evolve. It would be really lucky if you get there and shine a light and you have a bunch of purple bacteria. It's purple because I walked across the hall to a friend and asked him what color bacteria was on Europa when we were getting this art made. He says purple, so right. It's purple. Right. But you also wait and you filter the water as it flows past you. There are probably pretty strong currents on Europa related to, one, the fact that the ocean is very deep, but two, that there's this tidal flexing going on. And so you're lucky that a lot of material will be moving past you. And so you continue to filter that and look for it. And so the science you do can be everything from monitoring to see if you found cell structures or DNA, or perhaps more ubiquitous biomarkers like changes in the chemistry, or life tends to eat. If you have two molecules that are a mirror image of each other, it tends to like to eat only one of them and not the other. So if you find that you have a disparity in the amount of mirror image molecules, that can help you determine whether there's life in the environment. One thing I think would be really fun to do, though, and probably the least scientific part of talking about these measurements, so error bars, on Earth, when you go to the deep ocean, far from where you get life, the easiest way for life to communicate is through light. And so I think it would be fun, though, again, not necessarily a championed or most scientific experiment, to turn off the lights and see if anything's glowing.
Right. How's your time? Because I think we've got a few more topics I'd love to get through. Are you all right?
Oh, yeah. I'm having a great time. I'm happy to hang around.
Okay, great. All right. Probably another, say, 20 minutes or so. So then, now you mentioned that some people are considering mobility. So what if you were carrying some sub-probes, some cryobots, some way to get out there into the ocean and be able to return that data back? Where would you want to go and explore?
Yeah, such a great question. Well, the answer for me for that is the entire ocean of Europa.
Right. So take an entire ocean's worth of cryobots. Fine.
Yeah.
We'll miniaturize it. We'll figure it out.
So I'll start it first by saying you don't get anything in thinking about these concepts without giving something up. If you want to bring mobility, then you usually have to give up the amount of time it takes to get you there, or the amount of instruments you can carry or something. But there are different concepts exploring those traits. And there's the really cool, like, Georgia Tech and Cornell ice fin robot, which is usually lowered down a borehole made by hot water drilling after the hole's open. And it can swim around in an ice ocean interface and get these really cool profiles of chemistry and look at melting. And so that's kind of one end member where your whole cryobot becomes a mobile platform. There are also end members that think about, what if you just give a little bit of that payload space to something with some mobility? So there are things like Brewy. It's a buoyant under ice rover that could come out and crawl along the ice ocean interface looking for things. And if you look that up, they have all of these really cool pictures where, like, they've gone to ice sheets on Earth where the sun is just barely able to get to the bottom of the ice. And so much like Europa, where things might be waiting for oxidants, you have things waiting for that sunlight to do photosynthesis. And so you actually get these algae mats that form on the base of the ice, and they'll go crawl around this Arctic ice with Brewy.
Yeah, we've covered this. It's a rover that crawls around on the underside of an ice sheet, but so everything's upside down. But when you sort of envision it, that I guess you would roll out this rover as if you were on the surface of Mars, but it would be buoyant enough that it would be held to the surface of the ice, whatever it is, and it would then be able to crawl around the surface of the ice. Everything's upside down, searching for interesting features, life, boulders, rocks, but everything is upside down. It's such a weird idea, but I love it.
Yeah, it's very cool, right? Because the buoyancy force is bigger than gravity there, so it just sticks to the top.
Yeah.
And then there are sort of, you can keep going down with the scale. A concept I'm involved with called SWIM, that's funded by NASA, is looking at, well, what if you just bought a bunch of really densely packed micro robots that might passively move in the water or might swim around, but with, like, say, a very basic salinity sensor each, and you just release these into the ocean? What might you learn? And so the kind of science you can do really depends on the kind of mobility you can bring with you. I think that I think you would fundamentally change how we think about other worlds by getting to the ocean. And so if you can do bonuses with mobility there, it's fantastic. And I think as people keep working these concepts and we keep getting a better understanding of how to make them more streamlined and more efficient, there's a chance that we might figure out how, even in early cryobots, we could start thinking about mobility. But if it were up to me, there are two places I would want to go. The first is, in one place on Europa, there is definitely a thing that seems to be subduction, where a big icy plate near the surface seems to have gone down into the interior, that geologists working in the field found in 2014. I would definitely want to go beneath that in the ice and see if there's anything there waiting. If I got to go to the seafloor, which is a much harder problem than the base of the ice shell, right, there's a lot of pressure at the base of a 100-kilometer deep ocean. It's about the same pressure as at the base of the Marianas Trench. And so if you go down there, I would love to see a hydrothermal vent.
Yeah.
But, I think that because I think a lot of the eye rolling in the field from talking about getting to the ocean comes from this idea of, all of the difficulties involved and the vast number of unknown environments and things. I think that there's the potential to work on mission concepts that could be employed on the order of 1 or 2 decades rather than a century, that are capable of getting to that ice ocean interface and then thinking about where we go next. And so there's this group called the Network for Ocean Worlds, which is within the NASA astrobiology program. And we published a white paper recently talking about what ocean worlds exploration could look like. And I really like this idea that, you fly by and map them, or you go collect material from their plumes to understand what's in the ocean. And then you start going down. You go down to the ice-ocean interface, and after that, you think about exploring deeper.
So what is the sort of big technical uncertainty? What is the, when people roll their eyes at the idea of a melt probe or a tether, and you're like, no, that's mostly a solved problem. What's the one that you hope they don't, the one that you are pretty anxious about, that is going to require a lot of technical investigation?
Yeah. So I'll start by saying that I approach this problem as a pessimist who thinks Europa is going to be too hard to do this.
Perfect.
And so
you can't be disappointed
in some ways, it can be really frustrating for all of the fantastic, engineers and technologists I work with, and sometimes the scientists I work with. But in other ways, I think it really helps us hone what the problems are. So I think the biggest perceived risks are kind of the things we're touching on. First, that you can't bring enough power to do it. And I think we understand now that you can, or at least that there are avenues to develop power systems that could be used in a concept like this. And when I say we think that, right, there's a group of people across different companies and labs and organizations, both in the US, but also in Europe, who's become a leader in cryobots, and work out of China, thinking about cryobot development. There's a large community that really sees the potential here and isn't as scared. I think outside of that community, the biggest perceived risks are that we don't know enough about the ice shell. So the real big contribution I make is I think about all of the different ways the ice shell could be challenging. Intense radiation at the surface, and how do you communicate, or how do you keep an antenna alive while doing that? Intense geologic stresses and strains in the interior, thick ice shells that take a long time to transverse, even the potential for diffuse ice-ocean interfaces that might be a little mushy, and thinking about how to overcome all these challenges. So we don't know the answer to a lot of the questions about what Europa's interior is like, but we can put bounds on what, we know the box that the answer has to be in. It's kind of like there's an infinite number of numbers between 1 and 2, but none of them are 3. And so we don't have to engineer against 3. And right. I think part of what's helped me retire my own skepticism is being able to work against these more difficult bounding challenge cases. And so I think the biggest perceived risk is the unknown structure of the ice shell. But that is something we work on a lot and are pretty confident there's a solution using melting and water jetting, and potentially cutting, depending on how our understanding of salts in the ice evolves.
But I guess I imagine like a juiced up version of InSight's mole, where they couldn't even get into they anticipated that it would, they weren't sure how deep they were going to go, and they suspected they might hit a rock, but they couldn't get even more than a few centimeters into the regolith, and it just didn't work.
Well, if they had brought enough plutonium to melt the rock, it would have.
Sure, yeah, I guess so. Yeah. They just were going about the problem wrong. Yeah, bring the plutonium, melt the rock, just go right down to the core. Sure.
Yep, the real way to retire risk, which is, I guess, our way of saying to know that you're going to be successful. The real way to retire risk against not being able to get to depth is by bringing more heat with you.
Yeah.
And so you can make assumptions like, what if we're wrong about the thermal properties of ice or its mechanical strength? Or what if we're wrong about the temperature structure? And you can say, well, what if we're twice as wrong? Right. Or and you can design against that instead.
But couldn't you just drop a RTG in a sphere onto Europa with Europa Clipper? They just talked about the lander. They want to bring a lander for Europa Clipper. Couldn't you just bring an RTG in a metal sphere, just drop it, and then Europa Clipper could just keep checking to see how deep it is over time?
Interestingly, you're not the first to suggest that.
Okay.
So I have some thoughts.
Yeah.
First of all, we're trying to launch with Clipper in 2 years, so please don't go adding things to it.
I'm not Congress. I'm not
yeah,
adding a lander. I'm talking about a 1 kilogram ball of plutonium. How hard could that be?
So, surprisingly, but right now, actually, Europa Clipper is solar powered, and there's a big difference between going with a radioisotope power system and going without one. But Europa Clipper is set in stone and moving along.
Yeah.
But thinking about potential opportunities in the future to drop things, there is a whole field of study about icy impactors, things that are dropped from orbit instead of requiring landing. Right now, the sorts of challenges are, how do you not crush anything inside? But I get what you're asking. Like, it could just melt and maybe you ping it with a radar.
Yeah, just to see if the interior, moving through the interior, is as you expect. That's it.
So I'll say that the biggest difficulty there is with the amount of heat you can pack in a certain shape. You said earlier that you had read that the skinnier you make it, the faster it goes. And the real reason, right, it's not so much the friction of ice, but imagine standing on the surface of the ice shell and looking, 10 miles down at the ocean. You have to melt all of the ice in the footprint of your vehicle between you and the ocean. So as the radius of your thing gets larger, the amount of ice you have to melt gets larger squared. And it turns out that spheres are a really inefficient form factor for getting through ice. So the biggest issue is you can't get the heat density.
Right.
If you solve how to get a melt probe on the surface of Europa without landing it, give me a call.
Sure.
I haven't gotten there yet.
Yeah.
But the reason that they're these tube-like structure is because it takes some time for the water to freeze again behind you. And so you kind of want to fill up that entire volume of liquid with your robot, however much you can get without freezing. And then you just keep the diameter thin so that you don't have to melt as much ice.
Yeah, but I'm just thinking about ways to reduce some technical risk, but I totally get that. One other issue that people talk about is this idea of planetary protection, that anything we send to Europa is going to be filled with filthy Earth bacteria. How do we prevent it from infesting a pristine European ocean?
Yeah. That is, so getting back to the issues people see as the major risks, and there are one or two more I want to touch on.
Sure.
But this one, planetary protection, is a really great point. Europa is a class 4 world, which sounds very Star Trek-y, but it just means that it gets the highest class of planetary protection. And so you can, there's a lot of room to talk about the philosophical reasons for planetary protection. The very practical reason is you don't want to introduce stuff from Earth, because if in the future we were to find life beyond Earth, we want to make sure we didn't bring it. And so the biggest concern is making sure you're clean from Earth life so that you don't contaminate your environment. It's hard enough on missions like Europa Clipper, which are never intended to contact Europa at all, right? And ensuring that they're not going to somehow end up on a surface of a geologically active world that then incorporates their stuff and sinks to the ocean. And so, right, there's this idea of, if you're going to the ocean on purpose, how do you stay clean? And it's something we've actually given some thought to. Us and others. Our group has had a talk on it at like the Astrobiology Science Conference, AbSciCon. There are a lot of different options. First of all, there are things you can do in the laboratory as you're assembling items that you would do with any spacecraft. Two of the biggest ones are you swab things with alcohol, and something called dry heat microbial reduction, which just means you heat it up until everything dies and the spores fall apart. But, it's really difficult while you're on Earth to get things clean enough to intentionally put in an ocean. And so there are other options that we're exploring. I'll definitely note that there's, no formal ruling or anything by NASA's Planetary Protection Office that says you can do planetary protection on this kind of thing, but it's something we're studying and NASA's investing.
Right.
So one of the big things that can help you a lot is the potential for in-flight sterilization. So you can imagine that you have a long wait between the time you leave Earth and the time you get to Jupiter. It can be really difficult to do sterilization quickly on Earth with heat because you need very high heats at relatively short times because you're building a spacecraft while you're doing it. If you have years in space, you can go to a much lower heat over a much longer time. And as we talked about, you can't turn these power systems off if they're radioisotope powered. And so you have to find some way to, if you're not melting kilometers of ice, get rid of that heat. So if you make your heat radiator to space, the way you're getting rid of all of this excess melting heat, if you just make that a little bit less efficient and warm things up, there's the potential that you could do a lot of great planetary protection, bioburden reduction, so reducing the number of cells and spores, by having a really long bake on your way there.
So you're like Parker solar probing yourself, your own spacecraft. Yeah.
Yeah. Though I like that. There's still a really big problem of you're never going to be perfectly clean, and someday you're going to be sitting in that ocean. Well, if these kinds of concepts are flown in the future and they're successful, someday you're going to be sitting in that ocean. And then it's a lot more difficult. So for example, for the Europa Clipper mission, the NASA Planetary Protection Office used something called a period of biological exploration. Europa is probably geologically active. Stuff on the surface is probably someday going to get to the ocean. And so you'll never have a scenario where after an infinite amount of time, you're not in the ocean. But there's this time scale of like 1,000 years. You have to show you won't contaminate it for 1,000 years. And that's because in 1,000 years, we will probably either be able to clean it up or we won't care anymore. And so you can imagine hanging out in seawater for 1,000 years. Like think about shipwrecks that are 10 years old. It can be really difficult to stop water from penetrating all your subsystems and stuff. So we've not worked the problem as vigorously for what you do at the end of life. You don't want to risk falling to the seafloor where you could implode and introduce stuff. For the Europa lander mission concept, one thing they were exploring was something they called terminal sterilization, where in the end, essentially, they just melt the whole spacecraft. You can imagine, you just turn off the coolers when you're in the ice shell, and you're going to get very hot very quickly.
Right.
So it's a big issue. It's not a solved issue. And, there was a point where I was working these concepts that I had what I called the magic steps I thought were needed in order for something like this to be feasible. And even planetary protection now, I no longer really think is a magic step. I think it's solvable, but it's a problem that needs to be worked.
Is that the question mark when you're gathering underpants, gnome underpants?
Yeah.
Okay.
Well, I think I've gone from 3 question marks down to maybe 2.
Right. Okay. Now you mentioned a couple of other things that keep you up at night. What are just another one of those risks that you think is pretty significant?
Yeah. So, like I said, we've thrown, we as in the full community of people thinking about all these different concepts have thrown realistic Europas at them, where we're understanding how to even operate, fiber optic tethers in realistic geologic environments. One of the most difficult things is radiation survival. For a concept like this, you have to be able to communicate with Earth, which means something has to stay on the surface. And as we've discussed, while the radiation is great because it's a big part of Europa's habitability story, it might also destroy anything that you want to leave there. As I mentioned, Europa Clipper is only dipping its toes near Europa's orbit for a few dozen flybys, about 50 flybys, but spending most of its time far away from the radiation. So one of the challenges is going to be on top of your cryobot, you probably have to have all of the long-term landed electronics you need to communicate with Earth, everything but the antenna. And so we think about melting down and maybe after the first 10 meters, you leave behind the lander electronics with its power source. And so radiation survivability, somewhere like Europa, is a really big question. But one difficult step is someday a concept like this gets flown and it's sitting on the surface of Europa, and at time 0, it's sitting there, and at time 1, the ice is closed behind it and it's inside the ice shell. And getting from time 0 to time 1 can be a little difficult. You can imagine if you try and heat up the surface, there's no atmosphere, and so there's no stable liquid water. The water molecules are just going to blast out of there through processes like sublimation, where it goes from being a solid to a gas instantaneously. And so you're just kind of eroding a pit beneath you. You can imagine cutting, drilling down, but there's a big question of how you push. You're in a low gravity environment, and if you push hard enough to cut into the ice, you just push your spacecraft up and spin it. And you can't use water jetting before you have water. And so it's called the startup problem. There's a lot of people thinking about, for example, do you have to like bring collars to build up your own atmosphere through sublimation that allows you to then melt or something? So the aspects in the very near surface are something that require, I think, more thinking, and one of the things that keeps me up.
Right. And so it's almost like once you're a few meters down, then you're making water, you're sinking down, everything's fine. But to just go from literally the space to a few meters down is tricky, not to mention the brutal radiation environment that's bathing your spacecraft, and even whatever poor spacecraft has to remain on the surface throughout the duration of the mission. I forget, I researched it's like 1,800 times normal levels of radiation. It's brutal how much additional radiation is there on the surface of Europa compared to just space itself, which is already awful.
A good analog is sort of, it's extreme for different reasons, but the surface of Europa in a lot of ways can be like the surface of Venus, in that it's a really bad environment for spacecrafts.
Right.
Luckily, there's been a lot of great thinking in a bunch of different projects and concepts about survivability, but it's a hard problem. It could also just be that I understand the ice shell, and so like knowing your problems is less anxiety inducing than not knowing your problems. Maybe somebody more familiar with surface things isn't as scared.
Right.
But that one's difficult. I also thinking about how you get your data back to the surface can be pretty scary. Are some of the concepts we're exploring, for example, consider that if your tether is severed, if you lose that umbilical, and you're operating on these pucks alone, by the time you're in the ocean, if the ice shell is 40 kilometers thick, you might only be getting 100 bits per second. And so, 100 bits is not a whole lot of data, right? It's like a sentence or so. So at 1 sentence per second, you're trying to send back your 8K IMAX 3D movie of the space dolphins. And so there's probably a lot of work that has to be done in like compression and data transmission. But on that note, like one of the biggest overall challenges is going to be autonomy. When you operate a rover on Mars, you get to bring people into the loop all the time. You can stop the rover, you can all sit down around a table and find the shiniest rock and then upload commands to go drive there.
Right.
Not so for places like Europa in the Jupiter system, where you have a 2-hour light delay, and where it's very difficult to stop your probe or get real-time data back from it, right? You need to be able to react to things faster than it's going to be able to ask you to react.
Right.
And so there's going to have to be a lot of development in autonomy, which is sort of parallel with the hardware development. We have to understand how to sense the properties of the ice in front of us. Things that, if you end up with Cryobot that has something like pendulum steering, where you can make one side hotter than the other to move over long time scales, you might consider detecting salt layers and avoiding them or something. You need to understand when and where to do science. There are what we call triage science observations you can do. And that's something like looking at a camera. You can look at a camera all you want continuously forever. But if you want to do, for example, some chemical test for life, you might need to bring chemicals with you and have a limited number of areas or material you can do that with. And so you might need the Cryobot to autonomously decide when the triage data says, okay, it's time to use one of our only 3 shots at looking for so-and-so.
Yeah.
And so I think, the eye rolls that are coming from the environment and the hardware aspect, I think, a lot of those can be retired by socializing these concepts more and really socializing that it's built on 60 years of understanding of how these vehicles work. But the autonomy aspect is probably something that's new, but it's new across how we think about spaceflight and introducing more science autonomy into missions.
I mean, it definitely feels like that autonomy is being worked out with Perseverance. I mean, it helped figure out its own landing. It's doing a lot of its own thinking right now. They're practicing working in tandem with a helicopter, which is blowing my mind. When you think about what Dragonfly is going to have to do, it's going to be many light minutes away from Earth, and it's going to have to navigate in flight pretty much on its own. All right, so we're 2032. Europa Clipper has arrived at Europa. It's been a couple of years now. The new decadal survey has come out, and it's really just one page. Like, people have just wiped away. It's not 780 pages. It's one page. It's the 2032 decadal survey, which is explore the ice under Europa now. What is the what do you see as like the mission that is going to pull this off?
Yeah. So I'll start with like a couple caveats. A lot of really brilliant people in the field are thinking about this problem all the time. Like everyone, I have my preferred Europa that I hold in my head until Clipper gets there and turns Schrodinger's Europa into a real Europa.
Sure.
I have my particular concepts and all that.
You got beautiful maps of Europa now already in front of you.
So apparently they let me write the 2032 decadal survey, and now they're letting me talk about what the mission's going to be.
Yep, exactly. And they told everybody to just go home. There's only one person. Yeah, there's only one page in this decadal survey. What does the mission look like?
So if it's just me speaking as Sam, I think the answer is you have about 300 kilogram, maybe 3 meter long, so 10 foot long, 10-inch wide probe. And you get a Starship too. Oh yeah. Oh well. We'll start with
and
SLS.
Unlimited funding.
Yeah. Well, then I'm going with it.
No, personally, yeah.
So I think
begin the first part of the drilling,
but there's still a lag there, even if you can launch the mass. It's where our technology can be 20 years from now.
Yeah, I'm not giving an antimatter drive. No, it's a Starship.
So I think the mission that I see, the sort of my concept for what you could do, you have a probe about on this scale. It's I'm basing a lot of this on the Prime project concept at JPL. But yeah, so like 10 feet wide or 10 feet long, 10 inches across. You have a large radioisotope power system there. And you have, 20 or 40 liters worth of science equipment. If it's up to me, I'm bringing something like, the buoyant rover. And you have some good triage instruments for while you're in the ice, and some good life detection instruments. I think you launch, I would have said on SLS, but if you want to give me a Starship, on Starship, travel time's way faster. Mm-hmm. With a radioisotope power system, one thing you have to remember is that like radioisotopes decay. And so you get less heat the longer a mission goes on. And so the quicker you can get there, the better, because your clock starts ticking the moment your power system is made. I think on the way to Jupiter, which in our case is going to be like a year or two, with our SLS, our Starship,
fully fueled
for this idea. We do our planetary protection checkout. Because I had unlimited money, I have some science investigations on my lander. I like this idea of you finally get to Europa. You have to do something called deorbit descent and landing. On Mars, we do entry descent and landing, but there's no atmosphere to enter. So you stop yourself and you get to the surface and you have your autonomous sky crane. I think it would be really fun to turn your seismometer on as soon as you touch the ground that you've put on your lander. And you had this big cruise stage, sort of the spaceship that gets your spaceship to Jupiter. And it's going to be traveling, 5 or something kilometers a second. So as soon as you get your seismometer on, I'm going to let that orbit Jupiter and then smack in and give the ice shell a good ring so I know how deep I'm going to be going. And then I think you spend as little time as possible, on the order of weeks, doing a surface checkout operation and getting yourself in the ice. You bury your electronics. And I think the most likely case is then you settle in for like a 4-year-long transit through the ice shell. I personally am really excited about what you could learn inside of an ice shell. Sort of the boring geology reason is we talked about this lava lamp convection that can happen in solid ice. On Earth, it happens in solid rock. And so you get hot rock near the core mantle boundary that over geologic timescales, so very long times, ascends because it's hot. And so it's buoyant and it comes up and cools off and sinks back down again. And this is incredibly important to plate tectonics and life on Earth and everything else. But we're never going to drill to the core and get to see all of the material properties and like the sizes of the individual little mineral grains as we go down. You could totally do that on Europa.
Yeah.
And so I'm going to get to see a profile through the solid interior of a planet, and that's never happened before. And then you get to the ocean. I think that if you can survive and keep recording data on the order of months, that's great. I really hope the answer is you get to the ice-ocean interface and it's obvious. But I would spend a few months really intensely looking for signs of habitability and life. So if that was a concept that we got out of some future decadal survey, I'd put a little bow on my career afterwards and maybe name a pet I met on Europa and retire pretty happy.
Well, it's almost guaranteed. We can definitely put in a good word for you. Well, Sam, it's been an absolute pleasure talking to you about this concept. And as I said, this is one of the ideas that people are very excited about on this channel and ask me all the time. And it was wonderful to be able to ask those questions to you and get your answers, which were terrific. If people want to keep track of your work and sort of imagine that day when we're going to be able to see under the ice on Europa, what's the best place to do that?
It's a good question. I'm pretty easy to find in general if you type Sam Howell and NASA into a search bar. I have a Twitter that's at Stokes_flow. Stokes flow is actually the lava lamp-like process that happens for interior convection. But yeah, I would say those are the two locations. As the Orca project ramps up, we'll definitely be creating a social media presence for that and be talking a lot more about how we're doing an analog dive into a planetary water body on Earth.
Fantastic.
And so I think to your point about this coming up a lot, one of the biggest takeaways I'd hope people would come away with is that there are a lot of very serious scientists and engineers and technologists that are really critical of this concept, that are working these concepts to make them more possible. And, NASA has played a huge part in keeping that going. There's a large international community. And so sometimes it feels like the biggest barrier to this can be the sort of laugh test. And I think, we're nearing critical mass where these kinds of concepts get past it, and it becomes more of a discussion of the magic steps, but like the key critical questions.
But there are a bunch of those, right? Like I think about James Webb as one example, and the idea of detecting gravitational waves is ridiculous. and yet they figured it out and they were able to pull it off, and now it's routine and now it's expected. And so as long as people keep coming up with ideas why they think it won't work and you're able to sort of process them, I think it's a good direction. Well, Sam, I don't want to take any more of your time. Pleasure talking to you. I will provide a link so people can find out more, and good luck. And if you do meet a European dolphin, please let us know.
Oh, absolutely. I'll name it Fraser.
Awesome. All right. Take care.